Okay, in this example we're going to look at applied differentiation. Here we are given a problem where we have a rectangular sheet of metal. The dimensions are 360 millimeters by 240 millimeters, and it has 4 equal squares cut out at the corners. The side of each square is x millimeters, so each square is x millimeters squared. Now the first part in solving this problem is to determine the volume of the container that can be made by removing x squared out of each corner of our metal and folding the sides up. So we have the length, the breadth and the height for volume. So the length will be 360 minus 2x. The breadth will be 240 minus 2x. And the height, of course, is this part here, which we know to be x. So our formula for volume is starting to take shape. Next we just simply multiply our formula out. So 360 times 240 gives 86,400. 360 times 2x minus 2x gives minus 720. Minus 2x times 240 is minus 480. And minus 2x times minus 2x is plus 4x squared. And remember, we still have to multiply on the x, which is the height of our container. So we multiply those out and we simplify and we get an equation for volume. We're now representing volume in terms of x. And this is important because when we differentiate, we find the rate of change of a function depending on a variable it depends on. So we can find the rate of change of volume with respect to x. So we differentiate our equation and we get 86,400 minus 2,400x plus 12x squared. Hopefully you can all see how that came about. We differentiate 86,400x, the x disappears. Minus 1200 times 2 is minus 2400. Take away 1 from x squared, we get x. Here we bring the 3 down, multiply by 4, we get 12x, and we subtract 1, 12x squared. Hopefully that makes sense. Now, when we have a gradient function, that determines the gradient of a graph. So this could be a positive gradient of say 5. This could be a negative gradient of minus 5. This might be a negative gradient of minus 8. This could be a positive gradient of plus 8. When we have a turning point, dy by dx is equal to 0. So it's neither rising or falling at that point. In our case, we have a formula for volume. So we want to see where volume with respect to x is equal to 0. Because that tells us we're at a turning point. And if we're trying to find the optimum value of x for maximum turning point, we want our maximum volume, we want to determine what value x is when the gradient function is 0, when we're at a turning point. So we set our gradient function for volume equal to 0. So what does this formula look like? We have x squared, we have x, and we have a constant. It is of course a formula that we can solve using the quadratic formula. In this case, a is 12, b is minus 2400, and C is 86,400. So we simply plug those values into the quadratic formula and we solve for x. Quite a bit of work in this part, well worthwhile pausing this video and working through it yourself. Remember that the 24 in the bottom line, which comes from 2a, 2 times 12 is 24, remember that that divides into both the 2400 and this part here. Working through the quadratic formula, we get two possible answers, as always. Only one of these, however, is practical. For example, if we try to take 2x away from the breadth, and x is 152.9, that's not possible. 240 minus 2 times 152.9 would give a negative value. However, the other value of x is 47.08 millimeters, and that is possible. We can subtract that twice from 240, and we can subtract it twice from 360. So we will take that as our practical answer, and it's important that you state which of these solutions is your practical answer. So the optimum value of x then, to get a turning point, which we're assuming at this point to be the maximum volume, is 47.08 millimeters. But let's determine if that is a maximum turning point or not. Let's differentiate our gradient function again. So we differentiate for a second time. Now remember, we're differentiating this function here. So the 86,400 disappears. Minus 2400x becomes minus 2400. Plus 12x squared becomes plus 24x. So there's our answer to our second derivative. Now, if we plug our value of x in here, 47.08, and we work out our answer, we get a minus value. A negative value means that we're at a maximum turning point. So that's something you'll need to remember. Negative value, when you differentiate a second time and plug your value of x in, you're at a maximum turning point. Had it been positive, we would have been at the minimum turning point. So we can now conclude that for maximum volume, the optimum value of x, that we would remove x squared removed from each corner of our sheet of metal. Note the metal is of negligible thickness. The maximum value of volume is achieved when x equals 47.08 millimeters. But let's check that out. Let's plug that into our original formula for volume. We get a value of 182.5296.6 millimeters cubed. What I want you to do is experiment with different values. So plug in, for example, 50. Does the volume go up or down? You'll find that the volume will go down. Similarly, plug in the value, for example, of 40. You'll find once again the volume will go down, because we have found the value of x that gives maximum volume to be 47.08 millimeters. But once again, I asked you, try some different values. Try 48, try 46, try 100, etc. You'll see that this volume will reduce for all values other than our optimum value of 47.08 millimeters. Now think about other ways that this could be applied, what other shapes could be made, and what other formulas for volume may become relevant. because this is a good example of how we can identify the turning points for a function which represents the gradient function of a curve for volume.